Okay, we're going to do a little bonus lab here. We're going to head out in the hallway, and let's go to make a sketch of our situation so we know how to calculate our final result here. And right outside our hallway, what's really nice is we have a little handicap ramp, which in all new buildings is required by law so that it's handicapped accessible. For us, it's a perfect setup for doing a little energy transformation lab. Okay? And here's how it's going to work. We're going to have Tara take our bowling ball here, and at the very top of the ramp, it's just going to sit there. And it looks like it doesn't have any energy because it's sitting there, but you know better than that. What kind of energy is stored here at the start? Yeah, we have some kind of potential energy. I'm going to label that PE with a little I. What do you suppose the I stands for? For initial. Exactly. Okay? In other words, we had to lift this against gravity to a certain height. That makes sense? Okay? As this bowling ball rolls down the ramp, how's that energy transformed? It's converted into what? Into what? Kinetic energy at the end. That makes sense? And our potential energy pretty much just drops to zero because we hit the bottom of the ramp. So where's the bowling ball going to be moving the fastest? At the bottom. Exactly. Okay? And we're going to actually predict how fast that ball's going to be moving. We'll measure how fast it's moving, and we'll see how much we're off by. Okay? And you're going to see that we'll be pretty close given our range of error and our data collection methods. Okay? Exactly. Step 2, we need to list all our known and unknown information so we can figure out what's going on. Okay? So you tell me. Let's use a little common sense. What would affect how fast a bowling ball is rolling at the bottom of a hill? Okay? Exactly. The first big factor is that height of the hill in meters. Okay? Unfortunately, we have to do everything in metric units to be consistent, and it's harder for us because we live in America. Okay? Gravity would affect the final speed. On Earth, it's 9.8 meters per second squared. That's just a given. Okay? And by the way, I know it's hard to remember all these equations and constants, so on each of the problems page, I always put down the equations and the constants at the top. Okay? What else would affect the speed of the ball at the bottom of the hill? Use common sense. Okay? Yeah, the weight of the ball or its mass. Okay? And the mass of this bowling ball, it's a 16-pound ball, which is about 8 kilograms. We'll round it to 8 kilograms. Okay? Because it's roughly 2 kilograms in a pound. Okay, it's actually 2.24, but we'll round it off. Anything else we need to know? No, that's actually it. Okay? So we're going to actually go out, collect some data. We'll measure the speed of the ball, and then we'll calculate the speed. Okay? So what we're really trying to find is the velocity at the beginning or at the end. Yeah, we want to find velocity final. Okay? That's what we're trying to figure out. And we're going to assume that the starting velocity, the initial velocity, is just what? 0. Okay? It's going to start from rest. Questions? Okay, thanks for your help, guys. Here's the data that we got. Okay? The height of the ramp. Okay? Oh, I forgot to have someone actually grab a meter stick, but we measured it before. We're going to round it. Is that okay, guys? It rounds to about a meter. It's not exactly a meter, but let's just use easy numbers. Is that okay? About 1.0 meters. Okay? Yeah, in height. In height. Okay? And technically, you brought up a good question. The length of the ramp in real life affects the ball a little bit because of friction, but really, what's the key factor? It's the what? The height of the ramp. Okay? Or notice when you come in from the loading dock, you have a choice, right? You can either go up the ramp or you can go up the stairs, right? And in both cases, you end up at the same height. So it technically takes the same amount of energy to get to that point. Just the ramp makes it easier if you're in a wheelchair, right? Okay? And what we're going to try to find is the final velocity. Okay? I actually measured this with Duff's help. Okay? We found the velocity. Okay? We measured it. So I'm going to label this V measured. Okay? And like you guys said, it's just distance over time. So we did 5 meters. And let me check my stopwatch here. I timed it in 1.53 seconds. Okay? So if we calculate this really quick, we just take 5 over 1.53. What are you guys getting here? Like 3.2, we'll round it off. 3.27 meters per second. Okay? So in other words, this is what we should get ideally. Or not ideally, this is what we got in real life. What we're going to figure out is ideally what should we get. Okay? So in other words, if we didn't know this, we should be able to predict roughly what this is going to be. And you're going to see that it's going to end up being more, okay? And that's great. That's a great question. Let's figure it out, okay? So what equation do we want to use when it comes to energy? What's our big idea equation? Well, this is our new one here. The big idea is the energy that you start with has got to be what? The energy that you end up with, okay? And you could have work, you could have kinetic, and you could have potential, and you could have work, and you could have kinetic, and you could have potential. That looks nasty, right? Because it could be nasty, but in this case it's not. It's actually a lot simpler because at the beginning, okay, we didn't really want to push on it, so we're going to not have work energy, and it really wasn't moving. We're not going to have kinetic. Those are all 0. So at the beginning we just have what? Potential energy, yeah? And at the end, we're not really pushing on it. That's 0. It's not lifted above the ground because it's at the bottom of the ramp. That's 0. So really, what do we have at the end? We just have what? We just have kinetic energy. Okay? So in other words, in this case, all we're looking at is the potential energy of the bowling ball goes to kinetic. That's how we can figure out how fast it's moving. Okay? So how is this useful in real life? Well, when you design a roller coaster, you want to know how fast it ends up moving. All you have to know is how much potential energy you give it. Okay? So let's go ahead and calculate. How do you find PE? Let's look in our toolbox. PE is equation number 3, which is mgh. Okay? And I'm going to put a little I just to remind us it's the initial height that matters. And that's going to be equal to our kinetic energy, 1/2 mv squared. I'm going to put a little f to remind us it's our final speed. Okay? Let me go ahead and give me a little bit more room on the screen. I'm just going to substitute in our numbers from step 2 into step 3. Okay, to get our final answer here. So let me switch colors here. Step 4. Okay, mass was 8 kilograms for a bowling ball. G is 9.8. And notice we don't want to put in any units until the very end so we don't get lost in the math. Okay, as long as our units are consistent, we're okay. And that's equal to 1/2 mass, which is 8 kilograms. And we're going to solve for the velocity final squared. Okay? So now we'll get out our calculators and plug and chug. 8 times 9.8, you can do that in your head, or let's just use our calculators. I'm getting 78.4. So in other words, we start off with 78.4 joules of potential energy, and that's what powers our ball. That's equal to 1/2 of 8, which is 4, times the final velocity squared. Okay? Little algebra Mickey Mouse. How do we get VF by itself? Or you could call that X if that makes it easier for you. You're going to divide both sides by 4 to get rid of this. So we do 78.4 over 4. I'm getting 19.6, and that's equal to VF squared. So how do I get rid of this squared? Take the what of both sides? Got to take the square root, exactly, okay? And that'll give us VF. So on your calculators, a lot of times you have to hit the second squared button, okay, or inverse squared, depending on your calculator, and that's how you get your final answer. So when we do that, we're getting 4.4, let's round this up, 3, okay, meters per second. So in other words, ideally, if we start off with 78.4 joules of potential energy and it all goes to kinetic with an 8 kilogram bowling ball, it should end up moving 4.43 meters per second. We measured it to only be 3.27 meters per second. So what's going on? Why is it moving slower than ideal? Because in real life, you got to account for what? Friction and air resistance. And here's another thing, okay, is the ball is actually spinning, so some of that kinetic energy goes into the spin of the ball, okay? And in real life, bowlers, okay, it's big-time energy conservation and transformations. It's a lot of complex energy changes in throwing the ball, spinning it, having it slide, etc. there. We were just saying if we could predict how fast it would go using conservation of energy. And that's what coaster designers have to do. Okay? And there you have it.